Okay, welcome back. We are implementing what I'm calling a Parasitic C Compiler. I'll give us a quick rundown on the project. Um, so it is a compiler which um, compiles C to C, and it's written in C. And that's our first step, our first goal. And once we have that, um, we will begin changing the source language to be its own language, different from C. So I'll begin adding new features once the base compiler is already done. So there's a link in the description to the GitHub repo, um, and we've been working on the parser, and the lecture is pretty much done. We might need to add a couple more things, but we're working on the parser right now, and I'm using this Wikipedia article, which is the recursive descent parser um, uh, article, which has a really nice write-up of how to implement a recursive descent parser for very simple expression, um, for a very simple expression grammar. So that's what we've been working on. And I think last time I said I would go away and implement some more um, uh, simple things so that we could move on to the more interesting things. I've done some of that, and I've finished changing over expected identifier. Okay, I don't know what that's about. Um, I've converted all of the functions that we're using, sort of the old way of parsing all of these uh, over to the new way of parsing. So parse atomic type. Oh, these I decided to get rid of. Um, and it became clear that I need to start working off of an actual C grammar, and I'll try to explain why that is. But first, I wanted to briefly mention that I found a bug in what we had written last time. So this is probably best explained in the Boolean example. Yeah, so I've rewritten this a little bit. Currently, so previously I had been saying Lexer advance up here above the if condition and then testing token tag. I realized that that's not the right way to do it because, for instance, say if we have in like this parse expression, so this just parses a general expression, we have a whole bunch of if conditions one after another, and Boolean is like here. Imagine if all four of these called Lexer advance as the first thing that they do inside of the function. If that was the case, then we'd be, and then they test, token tag. Well, if this condition is false, then we return null and like move on to the next case right down here. And if that's the case, then we're mutating the state of the lexer each time we do that. And that's not what we want to do. We'd be like skipping through a whole bunch of tokens. So what we actually need to do is look at the next token tag first. And then if it matches the thing we're looking for, then call lexer advance. So I still get the feeling like there's probably a better way to have set this up, but that's just the thing that we have to remember. So the same thing happens down here when I'm parsing atomic type. So I'm just trying to parse, int, bool, character, and void, just the keywords. We do like an if condition up here with a whole bunch of things. Is it any of these keywords? And then we call lexer advance, and we're checking next token tag. So that's the one bug that I identified last time. So I fixed that. So yeah, we've got pound include. I think we wrote this on camera last time, and okay, interesting. So I'm saying I may have rearranged this. So let me re-explain the code a little bit. So we're saying if you do not accept token pound, then return null, so exit the function early. And then we're doing, so the first thing we do is accept, and then we're doing expect. All right, so it needs to have an include at this point. And then here we're sort of doing that anti-pattern that I just said we should be doing. We're calling advance first and then doing an if condition on like the tags. On token tag, not next token tag. So this would probably be better if we rearranged this and did next token tag. I don't think it matters in this case because we already know that it's after token include. I don't know. I think this could have led to a bug. So yeah, you want to check. You want to sort of peek at the thing peek at the current token, and that way you're not mutating the lexer. And if it's the thing you're looking for, then you can advance. Okay, let me commit that because that's important. Rearrange lexer advance and next token tag check. All right. I haven't come across that as a bug here. Like I don't think I ran into a test case where that bug made, or that that arrangement made a difference, but in any case, I'm glad we fixed that. Okay, let me quickly set a timer just so that we can sort of time box this. Let's give ourselves 40 minutes. And then we'll start talking about the grammar. So the reason we need to start thinking about the grammar is because I tried to implement parsing pointer types. And a pointer type has a type first and then the star afterwards. So this, if we were to quickly sketch out the grammar, it would look like something like this. A type could go to int or bool or char or void, or maybe what I will do is do non-terminals in all caps, or a type followed by a star. So, and this or notation is syntactic sugar in I don't know, most grammar specifications for this. So it's like this, and this is what's called left recursion, where we have a type is a type followed by something, and this is a problem for the parser that we're using, which can only handle a very simple kind of grammar. So the grammars that we can parse with recursive descent parsers cannot contain left recursion. And the reason for that is, if we were to try to write the function for this, is assume we have struct type pointer parse type and struct, you know, and we pass in the lexer. Assume we've written some function to parse types. Well, actually, no, actually, let me directly translate this grammar into this. So we would have the lexer, and then we would say if token type, token tag equals token int, then do something else if token tag equals token bool, then do something. Okay, etc., etc. Else if unfortunately, this might actually work. And it's supposed to actually break. So say we go through all of our cases int bool character void, and then in the else case we need to say, all right, try to parse a type and then get the star. So in this case, we would have to call parse type with the lexer, and we would get struct type pointer type equals this, and return type. So there's definitely a recursive call here. However, I think I've actually just solved my own problem, because we test for all of these first. So in this recursive call, we're not directly getting into this branch again. The problem with left recursion is that sometimes if we were to rearrange this, so if like this was the top if condition or something, if we had done it like this, then, you know, in order to parse type, the first thing we do is have to parse a type, and that's infinite recursion. So we can't have that. So what you need to do is you need to parse these things first, your terminal symbols first. Okay. So it's possible that I've actually just solved our problem for us, which would be great. However, I think we're going to run into similar problems in other parts of the grammar. So I'd like to look at an actual C grammar that's available online. I've put this link in the description as well. So this is supposedly a Yak grammar for ANSI C. Yak is a parsing tool, which actually, you know, I probably should be using, but we're going to continue with writing our own parser because I want to learn how to do a recursive descent parser. And so they give very nice names for all of these, I don't know, I guess you'd call them constituents. All of the non-terminals have like very nice names. So, oh, like unary expression, unary operator, cast expression, multiplicative expression, declaration, type specifier, declarator. So all of these have like specific names, direct declarator, which I kind of want to use because it's hard to name things and hard to keep track of everything. And a nice thing about this website is you can click on any of these and it will take you to that definition of that non-terminal. Or terminal symbol, actually. So like size of, this actually takes us to, this is still the same. No, it's a different page. Yeah, it takes us to the lex file. So this is the definition of the lexer. And size of is defined here as just the string size of. So that's nice. Okay. So let's look at the type should we do types right now, or should we try to do expressions? Let's work on expressions. So primary expression. Let's define primary expression. I'm going to delete all this. I'm going to delete this comment. And expression. Okay. Struct exper pointer parse primary expression. Struct lexer pointer lxr. Parse a primary expression. Okay. A primary expression is either an identifier, a constant, and I believe by constant they mean an int or a float. I'm not sure where character literals are. Is this a character literal? I guess it is, because this is a string literal. I'm not sure what L question mark means. So this must be a character literal. Okay, so they're calling those constants, an int or a character literal. And I'm going to include true and false in there as well. Okay, identifier, constant, string literal, or a parenthesized expression. In fact, why don't we just copy this over? So that we can look at it over here. Okay, so how do we parse an identifier? If lexer accept lxr token identifier. Then we need to malloc an expression. We need to set the tag to identifier. Exper ident, which we do not have right now. And it has data inside of it. Struct ident, which is just a character pointer. I'll call it value. Exper as ident value equals token. What's that? LXR arrow token. Okay. Return the expression. And I guess at the very end we should return null. Okay. Else if, or we could just do this. A constant expression. So what I'm going to do is I'm going to make a new function called parse constant expression, pass in the lexer, and it will return us either null or, oh, interesting. Okay, so it's going to return us either null or, or the expression that was parsed. Okay. And if that works, then we're just going to return the expression. Okay. So we need to define that. Parse constant expression. Parse constant expression. And this is just going to, I'm not sure why I put this above all of these. Actually, you know what? Down here, I've already written a function called parse expression, which parses an integer, a boolean, a character, or a string. Constant or string expression. Why don't we just do this? Constant or string expression. Okay. And then we can use that up here. I'm going to copy the signature above. Or maybe I should just move this down. To bottom here. Parse primary expression. Parse constant or string expression. Okay. So we've got identifiers, constants, string expressions. Now we need to parse a parenthesized expression. So we need to say if LXR next token tag is equal to token open paren. Then we're going to parse an expression. Okay, and this is not a primary expression. This is a expression, the full expression. So I need to define that function first. Parse expression. And here we're just going to call parse primary expression, I guess. We could check. So if we go here, it's either an assignment expression or this is the comma operator. Okay, what's an assignment expression? It's a conditional expression, which is a logical OR expression, or a ternary operator expression, logical OR expression, logical AND expression, inclusive OR expression, exclusive OR expression, AND expression, equality expression, relational expression, shift expression, additive expression. So a bunch of these we're going to skip. Yeah, so additive expression is here. And additive expression, it could be multiplicative expression, a cast expression, a unary expression, a postfix expression, and then finally primary expression. That's how we get all the way down here. So it's quite the chain. We're going to cut out a bunch of those because I don't care about like bit shifting operations at this point. But to parse an expression, we're just going to say parse primary expression, LXR, and return the result. Okay, so we get open paren. We need to lexer advance LXR because we just accept, in order to accept the open paren. We now need to say if expr equals parse expression with the lexer. If that returns non-null, In fact, why don't we can exit out. Maybe not. If we are able to parse just an entire expression, then we need to do lexer expect with lexer token close paren. So that's important, and then return the expression. So we've parsed, or we've checked that the next token is an open parenthesis. Open parenthesis. We've accepted that open parenthesis. In fact, it'd be kind of nice if we can move this up into here as like an and. To signify that it's like expression must have an arithmetic or pointer type. So we could change this to be Boolean. Sure, why not? And then you return true. That way, over in the parser, we can say stuff like this. I mean, that's kind of nice because then we've grouped the checking of the next token with the advancement. That way it's easier to remember that. Okay, and then we parse this expression. We parse an expression, and if we're successful in doing that, then we need to expect a close paren, and then we return the expression. One thing I'd like to do is go over to lexer expect, and instead of this p error, I think what we could do is say printf unexpected token got %s, or maybe we'll do expected %s got %s /n, and maybe we can do /n/t, and then I can actually print out the tokens that we're expecting. So the expected token is tag token tag names of tag, and the one that we actually got was next token tag. That's what we're comparing against. Token tag names next LXR next token tag. And how do I break this up? Oh, semicolon. Does it allow me to format things like this? It doesn't like that. Okay. That way, if we're expecting this and like it definitely needs to match this tag and we don't get it, then we print out what we got and what we expected. Okay. Could I commit this on its own? Improve part lexer expect error message. That's a good change. It's going to help with debugging. Okay, so now we're back here. Um, oh, and you know what? This, I don't need to do the if condition. Oh, I can actually just say lexer accept with the lexer token open friend. Oh yeah, I forgot about that one. Okay, yeah. So now we should be able to parse primary expressions. Okay. So I'm wondering here if I ought to like exit. I don't know. I think that would be good for now, and then so we'll make if you get an unexpected token, then we'll exit the program. I can change this later, but this is the most restrictive, so let's add this. Exit on lexer expect failure. Okay. And the reason I'm doing that is because I'm wondering if I could chain all of this stuff together into a single expression. And let's see how we feel about this. And close paren. And then all we have to do is just return the expression. Okay, I feel like that's a little more readable. Except an open paren, parse an expression and save it in an expr, and then expect a close paren. And if that all works, then you can return the expression. Okay. I like that. All right, so what's next? Postfix expression. I should also point out that the reason this grammar is written in a very particular and sort of odd way, I believe, is because it's sorted so that the precedence of operators is encoded in the grammar. So I don't have to worry about like if I follow this grammar, I don't have to worry about defining the precedence of operators. And also, it should be the case that it has already removed left recursion for us. So a postfix expression, right, like the first thing here is not postfix expression, it's primary expression. I mean, I don't know. This is kind of left recursion here. Postfix expression, postfix expression. So that's a little weird. Okay, but maybe it's sort of like the example that I started out with, where we were trying to parse types. And first you parse the sort of the atomic types, and then you can parse types that begin with a type. Maybe that's what it is. All right, well, let's just stick with the grammar as it is. So postfix expression. Let's copy all of this over. postfix expression. Parse a postfix expression. All right, so the first thing we need to do is we need to say, let's get struct exper pointer exper to start off with. First thing is we're going to check if we can parse a primary expression. So exper equals parse primary expression with the lexer. If that's the case, then we can immediately return the expression. Right? Yeah, a primary expression is a postfix expression. Okay. If that's not the case, I'm going to remember to return null at the very end. If if that's not the case, then we know actually all of these are going to start with a postfix expression. So we need to parse a postfix expression. Okay, so struct exper pointer child equals parse postfix expression with the lexer. And I think this should also be inside of an if condition. If child is non-null, right? If child is non-null, then we need to switch on the next expression that we get. So let's do, oh, and these do not have names. That's interesting. So this type of expression here is an array. This is an array indexing expression. Okay. So I guess we should do like a switch on the next operator, the next token that we get. In which case, why don't we switch on LXR arrow next token tag. Okay, so first we're looking for open bracket. Open bracket. Token open bracket. If you get an open bracket, then lexer advance, because we've just looked at next token tag. And then we need to say struct exper index exper, the index expression equals parse expression, right? With the lexer. We need to check that this is non-null, so I guess that means we should be doing if index. This is a little bad. Should we just return null early? Maybe. Oh, and I believe that we need braces around this entire body in order to declare stuff in here. Otherwise, we might run into problems with scope. So I will do that. Okay. We parsed the index expression. So that is this. And then we need to expect the close brace. Elixir expect LXR token close bracket. Okay. Then we need to build up the expression. So let's malloc an expression into expr. Yes. Expr equals malloc size of star expr. And all right, we've got about 5 minutes left in the stream, so I'm going to try to finish up this case, and then we'll probably call it for here. And I might work on stuff in the background, but just to keep these reasonably sized. Okay, so we're going to be building up effectively an array index expression. So we need to define that up here in expression. Ident expr array index. And we need a new struct for this, struct variant, called array index. And it has two members. It has a struct expr pointer called child, and one called index. Maybe it should be called array and index. The array expression and the index expression. Sure. Okay. And then we should ensure it knows how to print itself. Oh, we also don't have code for printing a literal expression. Case expr or identifier ident return fprintf s to out %s expr as ident.value. That's all we need to do there. And case expr array index return fprintf s out. So actually what we need to do is print out the expression, the first expression. So we're going to say display expression to the out file, expr as array index expression dot array. So first we print out the array expression. Then we print out open bracket, Then we display another expression, out expr as array index dot index, and finally we print out the close bracket. Okay, so that's how you print one of those out. And now we need to construct it. I should be like labeling these. Array index expression. Okay, so expr arrow tag equals expr array index expr as dot array index dot array equals the child expression, child. Expr as array index, array index expression dot index equals index. And finally, return expr. Okay, we are just about out of time for this video, so I think I'll end it here. I have not compiled this. But maybe that will be stuff I'll do off camera. Okay, so let's end it here for now.